From ContainerDays Hamburg, this video is proudly presented by Dux IT.
So I'm a co-founder and the CEO of NetBird, but I'm also a software engineer. At NetBird, we built an open source network security platform for engineering teams that helps securely and very easily access internal resources without anything like opening ports, security groups, and other firewall trickery. So one of the use cases that we have is Kubernetes access, so private Kubernetes clusters access without exposing this to the public. And one of the features that we have is DNS management. And that actually helps you to access private Kubernetes clusters by names, right? So not with IPs. And today, the talk is actually about that. And it's a sort of a story of how we approached this problem, what problems we encountered, and how we solved certain problems with eBPF and XDP. So here's the agenda. Briefly, the need for DNS in private networking. Then I'll show you how you can implement your local DNS resolver. In Go, it's not much code, but just some guidance on how you can do it. Then a very interesting part is the DNS port 53 issue on Linux and some solutions to that. And then we'll quickly look into eBPF and XDP and the solution combining these technologies together and pretty much how we put it together. So first, need for DNS in private networking. NetBird in the core of NetBird lays a high-performance WireGuard network. It's a peer-to-peer network. And in private networking, specifically in peer-to-peer networking, there are machines that are establishing direct connections, and there are agents that are running on these machines. So, sorry, the agents is reserved by AI folks, so client applications. And these client applications, they establish direct connections. In order to find each other, they need some IP addresses. These are the private IP addresses. Let's say it's a laptop on the left side, a server on the right side. And you can assign these IP addresses manually, or there is some sort of coordination server, that's the case of NetBird, that sends this configuration and assigns the IP addresses. And to make it even more convenient, this coordination server can send a private name that is also assigned to each of the machines. And the task in the end, and our task was to just do this simple thing, resolve a private name into a private IP address. So looks like a, I don't know, dictionary or a map in Go, and very, very easy thing. So how you can do it? First and most obvious solution is a centralized DNS server that you can run somewhere, I don't know, in the cloud or on your infrastructure that would keep these records, and the clients will call it to resolve the names. So this is pretty much like any public DNS resolver works. But for us, it wasn't an option because, you know, millions of the machines, it's also centralized dependency, some scalability issues, so we needed something else. And another alternative is to use a local etc host file. And probably, yeah, I see someone is laughing. It's not the best solution. Probably even worse than the first one. So the file can outgrow, and like who wants someone modifying their host file? So for us, the option was to create our own embedded DNS resolver that runs together with the client application that would keep the entries like name, IP pairs in memory, and then the client would use this resolver to resolve the names. Obviously, as software engineers, we didn't want to implement everything ourselves, so we used this library. Thanks to Mick Gibbon. If you know this library, it's a great library. It has lots of DNS-related code, so if you are willing to implement your DNS server, you can check this library. The interface looks very simple. It reminds me of a HTTP server. There is a listen, stop methods, and you can register a handler for a specific domain. In our case, it's a private domain, like private.network, that is resolved by this, or handled by this handler, and very easy, right? So you can take this and feed it into ChatGPT or whatever, and you can vibe code your DNS server in 15 minutes and then spend 2 weeks solving bugs. But in our case, we didn't spend 2 weeks in solving bugs because we actually implemented it ourselves. We didn't vibe code. Well, and these are two things that you actually have to do then. If you have your resolver, you run it on a port 53, 127.0.0.1, and then you need to configure operating system to point the DNS clients to this custom resolver, right? So you just add an entry, private.network should be resolved by this resolver. Brilliant, so no problem. So there is a problem. So do you know what this is? And actually it goes all the way down, so the picture didn't fit, the whole picture didn't fit here. So this is the Linux distributions timeline, and you know all these branches are certain versions of Linux, and we build software that should work everywhere, and we have to support lots of this. And sometimes things are hard-coded there. And in some versions of Linux, you have a DNS port 53 hard-coded into the operating system. So you literally cannot configure the system to point to another port. So, and obviously the problem is that if there is something that occupies this port, you cannot run your resolver, and therefore you cannot offer a service, you cannot resolve the private names. What we can do here, well, we call it a trick, but it's pretty much standard functionality. We can use unassigned loopback address range, which is going from 127.0.0.2, 127.255 to 55 to 54. So we can pretty much run multiple processes with different IPs, but same port, and Linux will allow it. So it will be resolved because it's a different IP, right? And the matching happens by a combination of IP and port. So sounds like a solution, but let's actually check it out. So that's a very simple code in Go. You see at the top we have 127.0.0.153, 127.0.0, 153 port 53, and I'm just running this program to see if I can listen on the same port, but different IP addresses. So it works, but there is a problem, and sometimes network administrators or system administrators, they change configuration of certain services, and they can listen on all interfaces. I love you guys, you know, and but sometimes it causes problems, and we have to be ready for this kind of problems. So to demonstrate that, I just added another parameter, which is IP address and port 53, right? So, and it doesn't work, right? So you can listen on the first one, but then the consequent ones, they fail by address already in use. And this is a pretty common situation, right? People change their configurations, and we have to make NetBird work everywhere, so regardless of what people run there. So what can we do? And we can use eBPF and XDP, and these tools really do magic. I love them. So shortly, eBPF allows you to run custom programs within the OS kernel, like a sandbox environment, and you don't change the kernel, you don't need to compile it, so you just inject your code, and it's executed in an efficient manner in the operating system. And now it's actually so efficient. So for network processing, packet processing, it's a great tool really, because there is no switch to the user space and things are running within the operating system and they're super efficient. That's why actually WireGuard kernel module is very efficient, because it runs within the operating system. So, and XDP is another beautiful tool that it's basically the quickest way to access network packet in a system. So it runs a BPF program when the packet enters the interface, the physical interface, and then you have access to this packet and you can process it right there. So what we're going to do with this? That's actually the whole solution flow. First, what we do, we run our local resolver here on the right side, and it's running on port 5053. So it's a completely different port. It's not a default port 53. Remember, it can be occupied. It's our actually interface IP address, and the port can be random, right? So this resolver listens on port 5053. Then we configure the operating system to point to a fake resolver, because remember, we cannot actually change the port 53 on certain operating systems. It's just hard-coded in the operating system. So we create this fake configuration, and now we have to make this the client request to actually understand that it shouldn't go to the port 53, it should go to port 5053. So what happens when you access any service, like Kubernetes service or maybe a server VM by name, or you put it in your browser, the DNS client calls the OS for a configuration. So how can I resolve this name? It receives the response, which is that fake resolver. Now the client makes a request, and our XDP eBPF program catches this request, and what we do, we just take and replace this port 53 by port 5053. And we have access to these packets right when they enter the interface. We override these packets, and we essentially forwarding traffic to this local resolver. So the local resolver reads the request, right, prepares the response, and then sends it back to the client. The problem is that the client doesn't know anything about the port 5053 because it's a different source. So it didn't send anything to port 5053, and it will reject the response. So for that reason, sorry, I skipped a little bit here. So for that reason, we need to override the port 5053, so it's the source port of our resolver, back to port 53. And if this all happens, the DNS client will receive the response, and it will properly resolve the name. So fake address and local resolver that listens on completely different ports. And that's an edge case, you know, and when you operate at scale, you have lots of these cases. So you have to deal with this kind of situations, and we created this logic, we built this logic specifically for these edge cases. This is how the BPF program looks like. And the first commented out section is actually the request way. You see that we are matching by port and IP. So we want to override the port 53 of the fake address to port 5053. We do it. XDP pass means everything is good, just packet can go further. The second section here is way back. So it's a very simple thing. We catch the port 5053, we override it to port 53, XDP pass, and the packet can continue. So, and this program is triggered by XDP. You may have noticed also there is a read settings function on the top. And here we use another great tool of BPF, which is maps. And this is a way to share state or maybe some parameters between the user space application and our client application and BPF program. So in this particular case, we are just configuring the program with ports and this IP addresses. And it actually can be other way around. So the user space application can read configuration or some parameters from the BPF program. And I want to give special thanks to the Cilion team. I don't know if anyone is here from this group. Thanks for this library, BPF2Go. It really helped to compile the BPF binary, BPF code, and then embed it into Go program. So maybe software engineers will agree with me here. This is a tiny feature. You can do it in a few hours. And these are the words of inexperienced product manager. And usually the simple things, or at the first glance, the simple things are actually not very simple. And this simple task to resolve private name into private IP wasn't actually that simple because of a number of edge cases that we encountered. There is, of course, more to that. There is some infrastructure around this code as well. I didn't show everything, but you can check it out yourself. The whole platform and this code specifically is open source. That's the first repo. And we also wrapped up everything for easy Kubernetes access in the Kubernetes operator. You can check this out too. Yeah, thank you so much for listening, and I'm open for questions.
Thank you. We don't have any questions yet.
No questions.
I can come up with a question.
Go ahead.
Or there's a question. Is there a possibility to override the DNS lookup address? Yeah, the possibility to override the DNS lookup address sounds like a security risk, is it?
Just like having a root, you know, it can be a security risk, but I mean, first of all, in our case, the code is open source, right? So it's always, you can always see what's happening there. And in the end, if you actually have root access, you can write your own program, like BPF program, and just load it, and you can override it, right? So, yeah, you have to use it carefully.
Yeah, that's true. Does this give every NetBird instance kernel-level network access of the host? Probably yes. Or not?
No. So it really depends on the operating system. So, and actually, that eBPF logic is the last resort that we use whenever we need to solve this edge case. Oh, in which system did you come across this issue? I don't remember exactly, but I think even Ubuntu 16 has this problem. But it's kind of old. But you know, in an enterprise setting, like when you have machines that are running like Ubuntu 14 or even earlier, this can happen. Maybe Maiken is the CTO of NetBird, by the way. He can
take it.
Hi. So we saw this issue on Ubuntu. The latest version, they have a default listener as well, which is like a stub listener for systemd resolve. We have other cases where people have actually DNS mask, or they have other resolvers that occupy the port. So we need to get around that and make sure that the VPN connection works for them. So these were the primary cases that we saw.
Okay, The other question is around, can I do this with IP tables? If so, what is the benefit of that approach?
Good question, yeah.
Yeah, so you can do that with IP tables. You can create NAT rules for that, and then override the source and destination. But then you have 4 rules, and it's like something that will be more transparent for the user, and people can override that, and then you lose functionality because maybe somebody cleaned something, or we would have to enable or disable firewall rules for systems that are running already.
It's also much cooler to use eBPF.
Yeah, okay, that's fair.
Then we can do this kind of talks, you know. Who likes IP tables? Yeah.
Yeah.
Yeah. Maybe in my previous life. Why write a new DNS resolver rather than using something like DNS mask?
Because we need to have something that is cross-platform, right? So we had the opportunity to use DNS mask on Linux. That would work fine. Maybe macOS if you have homebrew or you compile something for yourself. But then we decided, okay, we need to bring this in home. There was such a easy to use library there. And we decided to go for something that we maintain.
Yeah, that's fair. How does competing peer-to-peer VPN with DNS solve this? I don't know what the relation is here, but you probably know.
We probably know what you're talking about here. I actually don't know. So I don't.
I think other providers decided, okay, we're not going to bring the DNS management to a level which you see on NetBird. So we can, having our own resolver, listening to the port and having control of that, over that, we can route traffic the way that we need to. And sometimes you have part of the traffic should go to a specific resolver, part should go to the others. And having something that we can control via software is much easier for us to maintain.
You know, and sometimes the support for Linux is very bad when it comes to VPN, like old VPN providers, and we try to make it as smooth as possible. So, and I'm not going to name the providers, but probably if you worked with old legacy providers, you know what I'm talking about. So Linux support is always like Linux is not supported basically, and or it's really breaking. So that's what they do. Or they use a centralized solution, for example. We didn't want to go this way. As I said, it's a central dependency and scalability issues that we have to solve. And then there are some certain functional use cases that are much better solved in with a local resolution.
Yeah, the second one is probably more statement, like sounds like a terrible to find while debugging.
Yeah.
It can be, but I think that since we released this feature, eBPF ecosystem grow, and you have tools that make this much easier to troubleshoot. So we do have some debug messages. If you need to enable them, they will be enabled. We do also provide some user space logging to help this out. So you're not going to be in a blank if something goes wrong.
Yeah, it was actually challenging when implementing this to debug things, and there are certain like tricks also with the Linux, and it was hard to know what's actually going on. But
I think it's open source, if I understood it correctly.
Absolutely, yes.
So everyone can contribute if like the logging could be
absolutely,
improved.
yeah. So we didn't use BPF and XDP only for DNS. We have other cases, and it's worth checking the repo. You know, there are a few parts where you can see that code.
Yeah, and potentially could also ask something like AI or ChatGPT to improve the source code as well.
Yeah, and then fix the bugs for 2 weeks.
So I'm derailing the Q&A. Yeah. The next question would be, how would you characterize NetBird's unique value proposition compared to popular overlay VPN services like Tailscale or other zero-trust networking solutions?
I think all to all, these new tools, including NetBird, are competing actually with the old players, and we are all together going against this legacy monsters that do the remote access. And our value proposition is very simple. So we make it very simple to access remote infrastructure, including Kubernetes, also not necessarily Kubernetes, but VMs. And you close your infrastructure from the outside world. You don't need to expose it to anyone. And you don't have open ports. You don't have firewall configurations and so on. And it just makes life easier. And another point I want to add, we are fully open source, so you can take the code and actually take the whole platform and run it on your infrastructure. And then you will have the same solution on your own infrastructure as you use in the cloud.
Probably relates to that. Will this work on platforms like BSD or like operating systems, or I also saw Fedora and SUSE and others? So probably it will work anywhere, I guess.
So the eBPF part is exclusive for Linux systems. So on BSD we have a user space client, and we do other patterns to hijack the DNS traffic. So it's everything in memory, so we can actually we don't need to do this. We're still using a fake address for routing the DNS traffic, but we don't need to rely on eBPF there.
Okay. Where are the DNS entries for the local resolver coming from?
May I interrupt you for a second?
Sorry, yes.
About the BSD, so we also have plugins for pfSense, OpenSense, and this thing can work in more simple way on these platforms. So it's back to the operating system questions. And where are the DNS entries coming from? There is a central server, which is pretty much a metadata server that keeps the network configuration, and it sends this name. It generates and sends the names to the client applications.
Nice. How do you tell the system to use your resolver only for a private domain?
I can go ahead.
So with our resolver, we have rules that says that particular domains will be resolved by different IP addresses. And you can set things like, I want to have all the DNS queries resolved by a Google address or maybe Cloudflare, with the exception of this domain. So we wrote the traffic based on the domain there. And we just make sure that all the traffic goes through the resolver, all the DNS traffic.
And actually, if you want a specifics how we configure, there is a big if-then statement in our code, and that checks for how the DNS is managed on the operating system in short. And then it can use dbus as well to configure the system.
Then at the end, it's a not rule on the client, or did I miss something? Or not me, but the question.
I think it was a misunderstanding.
I think this is similar to the IP tables question. Yes, it's like a not rule, and it's just a more performant one.
Yeah, sounds good. And the last one is, do you think it's feasible to implement the entire DNS handshake directly in eBPF? Would remove the need for any server program? Interesting.
I'm not entirely understanding this. Do you?
Yeah, no, I don't think that we would personally, or as a team, we would not replace the whole resolver in our case with a eBPF program, because we try to keep things a bit with specific goals for the eBPF program, so they resolve. They do the job faster and rely on the user space code for that. So we don't actually duplicate the code too much or the resolver into different languages.
Perfect. Thanks for answering all the questions, and thanks again.
Thank you.
Thank you so much.
From ContainerDays Hamburg, this video is proudly presented by DAX IT.